Behind the ordinary objects which fill our daily lives lie some extraordinary stories. They are stories about real people finding ingenious solutions to problems you never even knew existed. And they take us to the four corners of the world. But what marvels of manufacturing do everyday objects hold? Glass, golf balls, the zipper, soft drinks cans, changing the tyre of a jumbo jet. 5 ordinary things, 5 extraordinary stories. Now revealed as we go behind the scenes, inside the machines, to find out, how do they do it? Invisible but essential to modern living. Countless panes of glass let in light and keep out the wind and rain. They are a crucial part of our urban landscape, and yet they're so incredibly fragile. Producing a crystal clear, scratch-free pane of glass demands delicate precision. Glass poses some engineering challenges that even the experts admit have them stumped.
Glass making is classed as a black art, and because there are parts of the process that we still don't really understand in great detail.
So, how do the modern-day wizards of glass manufacture do it? Welcome to Pilkington's in St Helens, England, one of the world's largest producers of flat glass. Their glass ends up in everything from car windscreens to skyscrapers. It used to be that molten glass was squeezed between rollers to get it to its size. But this left deep scratches which needed to be polished out by hand. Not anymore. Today, Pilkingtons make glass from scratch, without a scratch. And that takes know-how. It all starts at what is called the hot end of the production line, at the furnace. Here, the main ingredient is poured in: sand. Glass is more than 50% sand, and that's because of the way sand melts. At a scorching 2,000 degrees Celsius, sand, or silica to give it its correct name, turns from a solid into a liquid state. And, as if by magic, when it's a liquid, the molecules separate and let light through. The problem is, when it reaches such a high temperature, it's unstable, more like molten lava. So, one of the biggest challenges is finding ways to lower the melting point and stabilize the mixture. And that's what the other raw ingredients in glass, soda ash, limestone and dolomite, do. But in the furnace, the process isn't complete without one final ingredient, as crucial as the others and as abundant as sand: glass itself. Broken glass is called cullet. It's sprinkled into the sand mixture, and hey presto, this lowers the melting temperature to a more stable 1,600 degrees Celsius. And it's at this temperature that glass as we know it is born. But how do you turn molten glass into a flat and even plate of flat glass? The answer, rather surprisingly, is that you float it on tin. This method of making glass is called the float process, and it happens inside a chamber that has all the properties of a bomb. Inside here, ingots of tin are melted into a hot bath. The surface of the tin is perfectly flat, and stretching the glass over the top produces the same even surface. The reason for using tin is that it melts at a low temperature but has a very high boiling point, and because it's denser than glass, the two can happily share a bath without getting in each other's way. But approach with caution, because to stop the glass sticking to the tin, a heady mixture of nitrogen and hydrogen gases are used. The glass ribbon is now flat, but the hard work isn't over. These guys are about to change the width of the glass. To do this, it has to undergo a session of prodding and pulling, more grueling than a Russian massage. The top rollers can be angled, pushed and pulled, speeded up or slowed down. Outside the bath, the mechanics are manually changed to precise dimensions, an increase in speed, and the glass is narrowed and thinned. "600 tons of molten glass is continuously pushed through this furnace each day. It never stops, 24/7. Once formed, the glass needs to be cooled, but only very slowly. So, a series of cooling ovens spread over the 640 meters of production line bring it down to room temperature over a few hours. But here comes the jeopardy. If the glass gets cooled too quickly, disaster. It will be too brittle and shatter. As the temperature cools to levels hot enough to handle, the glass must stay perfectly clear. And it does, all because glass has a unique property. It doesn't crystallize, because incredibly, glass never becomes a solid.
Glass is classed as a supercool liquid. That in as much as it's never completely in a stable form. If you put it in your window, in 20 years' time, it'll be slightly thicker at the bottom than when it was installed.
So, the windows we look through are actually viscous. They are still technically liquid. What's the secret to this mysterious alchemy behind glass? What normally happens when a liquid is cooled to below its melting point, it solidifies and crystallizes. However, it's possible for some liquids to remain in their runny state, even when they fall below their melting point. Glass is one of those. And you can see through this supercooled liquid because glass molecules have a disordered arrangement, letting light through. The glass is nearly done. It's been heated, cooled, recycled, stretched and washed. It now must come face to face with the razor-sharp blade of the cutter. Automatic cutters score the glass into usable bits. Marked edges are snapped off, and off it goes to the warehouse. If uncut, one day's ribbon would stretch on a whole 30 kilometers. And this raises the stakes, because the speed of the glass continuously coming out of the furnace has to be matched by the speed of the cut glass coming off the conveyor and being shipped into the warehouse. And there is a very real danger that all this hard work could be shattered by one hurried slip. Now all the glass is upright and together. You can see that it appears green. This is intentional and something you should be grateful for. The green is iron oxide, which has been left in the glass. This stops light rays bleaching fabric and saves your furniture. Transporting oversized panes of glass around the world is no easy task. They must be carried by specialized trucks, which scoop up the holding racks whole, lock them into place, and off they go. For our offices, homes, windscreens, mirrors. To protect us from the elements, to shield us from danger, to give us a safer, better view of the world. It's incredible to think that something we consider a solid is technically a liquid, slowly shifting as we look right through it. You might think the business end of a golfer's swing lies at the head of the club. Certainly most golfers do.
And that's where it comes mastering, is trying to hit that club, the right perfect sweet spot with that ball in the right distance.
But the club barely touches the ball, A tournament can last 4 days. During that time, the competitors may hit the ball up to 300 times. But their clubs will only make actual contact with the ball for just 1/10 of a second.
Thank you. Thank you. Yeah.
However much players might talk about the design of their clubs, there's just as much ingenuity and science that goes into the ball. Titleist is one of the biggest golf ball manufacturers in North America. The company makes over 350 million balls a year.
We check every single ball.
To the untrained eye, golf balls all look alike. White, spherical, shiny, dimpled. But in fact, golf balls are precision pieces of engineering. How they're made can radically affect how they perform. The story begins with what's inside the ball. A solid piece of rubberized plastic, the core. This is where the core takes shape, the mixing conveyor. Here, a worker assembles a batch of raw ingredients that will eventually become the heart of a golf ball. These bags contain a kind of crystalline polybutamine. Polybutamine is the core's main ingredient. Getting the amount just right is crucial. Titleist make two distinct types of core, hard and soft. The different cores are easy to spot. And Willy Wonka would be proud because just like a candy factory, the ingredients are color-coded for a soft or hard center. But these are not sweets.
We'll make about 3,000 golf balls out of that.
Into a giant cooker, the embryonic mixture goes. And a few minutes later, it comes out looking like this. They call it the hot sheet. Cut and cooled, the hot sheet now resembles Play-Doh. Barely pausing for breath, workers ship the hot sheet off to the next part of the process. Here, the sheeting is sliced into strips. This extruder chops the strips into pellets. When cooked in core molding ovens, the pellets shrink and compress. The compression provides density, and density provides power. Core density on an average golf ball is equal to 40 kilograms of steel squeezed into a space just 4 centimeters in diameter. The core is a powerhouse of potential energy, the engine that drives the ball. By using a ball with a hard core, a golfer can be more certain of reaching the green. But length of drive is only half the secret to keeping golfers happy. If it's hit straight, it should go straight. That means achieving a good flight path. And the secret to good flight lies in the golf ball's surface. The ball's external housing is a 2-piece egg cup that holds the core. Think of it as a kind of nuclear reactor containment chamber, harnessing the core's massive energy. The cup is made of a durable plastic called polyurethane. Chip-resistant household paint contains the same ingredient. After cooking, the golf balls are beginning to look like golf balls. But they still need to acquire what is perhaps their most distinctive feature: dimples. On Cameron Diaz, they're an added bonus. On a golf ball, they're vital, because dimples make spin, and spin makes a ball fly true. Up to 500 dimples adorn each and every ball. So, how do the dimples get made? This is a moulding oven. Half-assembled golf balls are pushed up into hot dimple moulds. Freshly dimpled, the fledgling balls are sucked along high-speed vacuum tubes towards their ultimate destination, the finishing process that will make them the choice of champions. Aerodynamic properties are so important to a ball's final performance that they go through not one, but two polishing processes in an effort to further reduce drag. First, they must face the automatic ball buffer.
This is when the ball becomes a real golf ball. This is the excess splash of the ball that you see right here. It goes all the way around the ball. And after it's gone through the machine, you can see the finish line right there of the golf ball. And once it's sprayed and painted, it all blends in.
The second polishing comes when the balls are blasted by high-speed jets of water. Finally, after the balls have been branded, robotic sprayers apply a coat of aerodynamic paint. Golf balls almost look like satellites, destined for outer space. Spherical, shiny, dimpled. But they behave like ballistic missiles. The pent-up energy they contain is enormous.
It's so difficult to hit. I mean, you can see it, it doesn't move, and then when you swing at it and hit it, it doesn't always go straight.
And that's why golfers spend so much time trying to figure out how to control them. We don't usually give them a second thought, but they're everywhere. Zippers. Since they were invented back in 1851, the principle of the zipper has stayed the same. All that's changed is the early hooks have since become teeth. Each one unhooked by a plough-shaped wedge which pivots each tooth off the tooth below. They are deceptively simple pieces of engineering. But it takes 20 different manufacturing processes to make one. How do they do it? Astonishingly, 3/4 of the world's zippers come from China. And most of them come from just one place. The city of Kiaotu in the Zeeland province. The world depends on Kyoto to make 124,000 miles of zipper every year. It may not look like it, but the world's trousers are held up by these people. The biggest factory here is the Great Wall Zippers, or YQQ as they are known. And it's the beginning of the workday for the 1,000 people who are about to make the world's most common clothing accessory. It all starts with this stuff, tiny pellets of plastic. It may not look anything like a zipper now, but a transformation is about to begin, and these will eventually form the interconnected teeth of the zipper. Firstly, the pellets are melted down in an oven, then squeezed through small holes, cooled in water, and gradually stretched out over heated rollers into long threads. Each roller making them longer and thinner. It's critical that they all achieve the correct and even width. Otherwise, both halves of the zipper teeth won't fit together when they're finished. It's hard to believe this simple nylon thread will soon become zipper teeth. On a separate floor, the hidden secret to zipper making is being prepared. Spools and spools of cotton thread are being entwined to form what is called the central cord. When the zipper's done, you won't know this cord existed. But without it, the zipper would be useless. To find out why, you'll have to wait till the end of the next process. On the next machine, the nylon thread and central cord are about to be joined. They're spun through a heated screw that weaves them together, twisting the nylon into loops and inserting the central cord through the middle. Then the teeth are clamped round the cord. Now we have one half of a zipper, with a cord thread down the middle. Both sides of the zipper are fed together. If you look carefully, you can see two cords thread through them. So, why all this effort to have a piece of cotton running through each side of zipper teeth? Well, to overcome a problem. The zipper teeth may be attached to each other, but it's useless because it can't be attached to anything else. So, how do you get them into a pair of pants or a bag or a coat? In fact, anything. The answer is, it needs to be set into fabric. The next floor houses dozens of looms, weaving a fabric called tape that will make up the sides of the finished zipper. And there's a lot of it.
I help make over 600 million metres of fabric tape a year. It's amazing that there are so many processes behind the making of a simple zipper.
Now it is a matter of attaching millions of metres of fabric to millions of metres of zipper. And this is where both sides of the central cord reveal their magic. By being inside the loop teeth, the central cord is in the perfect place to sew the zipper into the tape. The two sides of zipper are then thread through another machine and sewn to the zipped up cord to create one long piece of zipper. The end product is huge lengths of different coloured zipper wound onto reels. Essentially, the zipper is made, except for the handles and slides. For these, tons of aluminium are melted at over 400 degrees Celsius, then pressed through an injection mould to make the casts. too hot to handle, these zipper slides are then dragged into another room. Here, a rolling bin separates them from the frame. As this batch continues rolling, on another floor, all the metal parts are being sorted and assembled. Handles and wedges are clamped together to make the slide. The reels of zipper will be cut to size and the slides attached when they're added to the finished object. Whatever they end up in, one thing's for sure. Zippers go through the same rigorous washing regimes that all our clothes are put through. But if the dyes bled or the fabric shrunk, it wouldn't be long before we resorted back to buttons to save the day. A sealed vat full of coloured dyes rises to a temperature and pressure high enough to lock the dyes into the fabric to make sure they don't run. And to prevent the fabric wrinkling up, after washing comes ironing. And a big lesson was learnt here. Huge steam-heated rollers are used to straighten out any remaining little creases. Steam rather than electricity is used on the nylon zippers because electric irons just melted the nylon. As the steam irons keep turning thousands of miles of zipper at the YQQ factory in China, another manufacturer, this time in Japan, has taken the zipper into the 21st century. If you check the zippers on your clothes, they may well have the YKK logo on them. But this Japanese manufacturer has also turned its zipper skills to all kinds of very unlikely products, ranging from aquariums to space suits and all-weather survival tents, like this. It just gets bigger and bigger thanks to every new addition simply zipping on, and zipping on. There is no limit to how big this can get. This tent is strong enough for people to walk all over it, as well as shelter inside it. All this thanks to the zipper. But their most unusual products show how the engineering behind the zipper has been used in modern-day mega construction. This is the Akashi Kaikyo Bridge in Japan. It's nearly 4,000 meters long, and at 280 meters, it's as high as the Eiffel Tower. It's the longest and tallest suspension bridge in the world. And right underneath the road, these engineers are doing routine maintenance. And how do they do it? With zippers. This rubber tube runs the full width of the bridge and is the ingenious solution to a problem that all metal and concrete structures suffer from. The road on the Akashi Kaikyo Bridge actually expands by up to 2 meters in a day, which is enough to make it crack and break under the strain. Every day leaves its mark on the metalwork. This is why a bridge has expansion joints built into the road surface. These allow it to move by the 2 meters necessary for it not to break. However, along with this solution comes a problem. All the asphalt and debris that cars bring with them could fall through the joints, 30 meters, onto fishermen and boats below. The tiniest piece of grit from this height could be fatal. The rubber tube collects all this debris. The zipper is the only durable and tough method of sealing it. All the zippers in the bridge are in places where the bridge is designed to move with the elements. For the next zipper, the engineers have to climb over 300 meters to the very top of the bridge towers. It's no place for someone with vertigo.
The zipper makes it easier for us to do checkups when we need to. The zipper also protects all the important parts of the bridge. Up here I get to look at the beautiful view. The big ships look so small passing under me.
It's August in southern Spain. Temperatures here can reach 50 degrees Celsius. The beaches are packed with hot and thirsty bathers, thankful to get their hands on a cold can of fizzy drink. What they don't know is what a miracle of engineering they're holding. In a factory at Seville, just a short distance from the sweltering Spanish beach, Can Maker Crown Holdings is running at full capacity. For this company, maximum comes as standard. The operation is big, but what strikes you most about can production is the speed. Every year, the world consumes enough cans to circle the globe more than 500 times. And that means deploying an awesome array of high-speed technology.
We're producing these cans with the same kinds of technology that are being used in the aerospace industry, but instead of producing one satellite a year, we're producing over 2,000 cans each minute.
So, how do they do it? The can starts life on a roll, a large reel of tin-plated steel. In the canning trade, they call it a coil, and from it are stamped thousands of these, flat discs known as cups. A monster die press stamps them out, 10 at a time, 250 per minute. Cut from the steel roll, the newly formed cups are launched on a high-velocity 3-kilometer trajectory arcing through the plant. It's going to be an incredible journey. First stop, these giant machines. They're called body makers, and they have just one task, to ram the cups into a cylindrical shape. It's not a gentle process. After some trimming work, the cup moves on. The next line of the process, fighting the war on rust. Cold drinks just love to corrode metal. The folks at Crown have found a way around that. Spray the inside of each and every can with an epoxy coating. The half-finished cans are now ready for branding. The staff here call it decoration, a quaint term for putting the logo on. The task falls to a computer-controlled printer. It's a kind of Formula One version of the printer on your desktop.
This printer behind me is capable of printing all 6 colors at speeds as high as 2,300 cans a minute.
But the ink is wet. Unlike paper, metal doesn't provide a good drying surface, so the cans must make a quick trip to the curing oven. After a little bit of baking, the relentless conveyors whisk the cooling cans onwards once again. Next up, the necker. It's what gives the cans their distinctive shape. The top of the can is simply pushed together until the neck is narrowed by 10%. The only reason for it? Yes, you guessed it, economy. This single innovation has saved over 6.5 million tons of metal. The cans move at breakneck speed here to an inspection area. This machine uses light to check for even the smallest hole. If the automated detective spots just one chink, the can is rejected.
The real challenge is to be able to produce the cans with such high quality because each one needs to be perfect.
Quality controllers carefully check sample cans for flaws. One can is checked every 15 minutes. It may sound excessive, but because of the speed of manufacture, this is a sample rate of just 1 every 30,000 cans. The rejects face a vacuum-powered fate. They're sucked away for immediate recycling. Cans have come a long way, both in this factory and in the last 70 years. They used to be heavy and costly to produce. Now, it's a different story. To achieve this incredible weight reduction, Crown technicians have worked tirelessly to make the paper-thin walls of a drinks can thinner still. They're now, well, a bit thicker than a human hair, yet they have to be exceptionally strong.
This can has to withstand 100 psi, or a pressure that's 3 times greater than that you'd find in the tire in your automobile. So it's really a pressure vessel.
The cans are now ready for filling. They head off to a neighbouring cola plant. With global demand for soft drinks at an all-time high, there is as much pressure on the factories that fill the cans up as there is on the plant that makes them. This filling machine dishes out a precise amount of cola at an astonishing 100,000 cans an hour. The empty cans are placed in the conveyor and then sped round the machine. The timing has to be exact. If they're even a millimetre out of sync, then the entire operation will grind to a halt. The clock is ticking. The cans have now to be hermetically sealed before the fizzy drink goes flat. The process happens so fast, you can only see what's involved in a lab. Enter the crowning glory of the Crown can, the top. Known as ends, these are placed over the newly filled can and then folded over to create a double seam. The double seam is so small, you have to project an image of it onto a monitor. But there it is. With seaming, a soft drink can is born. The thirsty sunbathers on this beach can relax. There are plenty of cola cans to go round. Fully recyclable, all that now remains is for this incredible product to begin its incredible journey all over again. They're fine in the air, mostly, and they're safe on the ground. But getting up and down really takes its toll on a plane. The average airliner travels a phenomenal distance, on the ground, up to 8,000 kilometres, taxiing and manoeuvring, touching down and lifting off every year. All that contact with the runway puts a lot of wear on one particular aircraft component, its tyres. The jumbo comes into park, and the two-man crew go into action. The operation begins pretty much the same as for changing an auto tyre, only everything's much bigger. And of course a car has only 4 tyres. A jumbo jet has 30. They're arranged in groups of 8 under the wings and nose, attached to what are known in the trade as trucks. In comes a jack to lift the truck. The jack looks pretty standard, but it has one very special design feature. It takes its hydraulic power from the pressure of the tyre that's due for replacement. As the tyre deflates, the pressure it releases is sufficient to lift the entire plane off the ground.
You have the pressure inside the tyre, and you use the pressure from the tyre to operate the hydraulic pump from the jack.
After jacking, the crew set about detaching the wheel. First, the mechanic unscrews a lug nut. Most aircraft tyres are held on by a single large nut, which is locked into place by retaining bolts. The practiced movements of the crew's hands make the job look routine. But the hub must be taken apart with a watchmaker's precision. The mechanics have to know what they're looking for. The only sign that a tyre needs changing lies in these, the grooves.
These grooves in here, so that's the wear indicator of the tyre. So if the groove is not visible, we have to replace these tyres.
As the tyre comes off, you can see how huge it is. A 1.5 metre radial, 0.5 metre wide.
They have to be very strong.
On the final approach, the tyres have flown for several hours in sub-zero conditions. On touchdown, the tyres accelerate from 0 to 280 kilometres an hour in just 1/10 of a second. Surface temperature hits 260 degrees Celsius. That's more than twice the boiling point of water. So, why don't the tyres explode on contact with the ground? Or implode during flight? The secret lies in what's inside them. Not compressed air like a regular tyre, but an inert gas, nitrogen.
So we fill these tyres with nitrogen because it's dry, there's no water in it, so it cannot freeze, and it is fireproof as well.
15 minutes in, the crew has got the tyre off and is putting a new one on. Time for a spot of elbow grease. This giant torque wrench will ensure the wheel is secure. The mechanic carefully checks the tension on each bolt. It's a crucial moment. If the bolts work loose, the results could be catastrophic. All clear. The crew is now on the home stretch. The tyre is inflated. The jack is lowered. The last bolt goes into place, held secure by safety wire. The crew has time for a quiet moment of satisfaction. Then it's on to the next plane and the next wheel. Since this programme began, worldwide 50,000 square metres of glass have been made, another 40 kilometres of zipper has come from the Chinese city of Dongguan, 40,000 golf balls have rolled off assembly lines, as have 25,000 soft drink cans. And somewhere, a jumbo jet has had 2 of its tyres changed. Even the most ordinary objects have an extraordinary story to tell. We only have to watch and listen.